Okay, if you haven't seen the D2L, I'm postponing the midterm and the program one class, just because we're slightly behind. And hopefully I'll get all the floating point in today, so that you can actually do your program. And I'll give you a weekend at least to work on that. That's all I have. We are doing number systems. So we did binary, we did decimal, we did hexadecimal. And I got you to a point where you're hopefully doing some of these conversions pretty solidly. So starting from here, plug in here. Here's another hexadecimal number, hex 333231. It's a very big number. In fact, if you actually do the math on it, is this 3,355,185? Well, yeah, if it was an integer. But this is actually 321 again. This time it's in what's known as the ASCII representation. So this is the third or fourth time we've seen 321. It's been in a lot of different forms. Here it is in ASCII. So what is ASCII? So humans, so you got a bunch of bits. They're 0 or 1s. But eventually we have to represent stuff like letters or symbols, right? So what we do is humans encode characters. So we basically overlay a semantic on top of these bits. So a blob of bits, if you overlay different semantics on it, will have different meanings. So in this case, yeah, if you put the semantic of treat that as an integer, then you get 3 million used in your program. But if you say, no, that thing, that's actually a string, then you'll get the characters 321. So, got your little device? All right, just hand it to me. So in ASCII, we basically encode pairs of hexadecimal digits as single characters. So each pair is basically 8 bits or 1 byte. So 2 hex digits is 1 byte. And typically bytes are the smallest unit of data that's addressable in a computer. Except for in your program, we're actually going to get into the bit level. But in terms of addressing data, we address it in the byte quantity, and then we have to do bit shifting if we want to get the bits. We have to do something else to get those out. Okay, so the ASCII system will map your byte values into individual characters.
But also, if you go into assembly, you can go straight into the byte level just naturally, right?
We'll get to that, yes. In your debugger, actually, you'll be able to go between all sorts of different formats based on the flag you send the print. So there's the print and the examine commands in the debugger. So I actually have shown you. So that was in one of those virtual lectures. You can specify the kind of formatting you want on the data in memory. So you go to an address and you're like, well, it's just a bunch of bits. Can you put a semantic on top of it? Can you show me the string? Show me that as a string, or show me that as an integer or decimal. Show me it as a hexadecimal value, as a decimal value, as a character. You can specify all of that in GDB. So the idea is that we have to put the semantics on top of it. And so this is just one semantic. And of course, this is a dominant one that's being used because it's used in URLs, in your web page encoding when you get back pages from the web, HTML. In email that gets transmitted. These are typically done in ASCII or in a related character set. Unicode or EBCDIC are other character sets that do this. Okay, so in this interpretation, you take these things byte at a time, and this is byte hex 31, hex 32, hex 33, and the semantic that we overlay on them is just a simple table. They came up with a mapping that maps these bytes, and there's 256 of them, because there's 256 code patterns in a byte, but it turns out ASCII only uses the low 128. So it's actually a 7-bit encoding. It's not really a byte encoding, but they throw away that most significant bit. And these are the values. So you see the decimal goes from 0 to 127, and the hex goes from 0 to 7F. Those are all 128 code patterns, and these are the and this is, you can barely see this, but like this image is Google searchable. You find it on Google. In this greenish thing are the actual characters that they represent. And so here you see the actual numbers, 0 through 9, the capital letters, and the lowercase letters. Okay. Yeah.
What's the purpose of some of the hidden encodings that are between hex 0 and 31? Or
0 to 31, these are special things like beep. There's actually a character. If you send it in an email, it'll try and get the terminal to beep. Or there's other special symbols like how do I know when to finish the interaction? That's a special end of file character. These control.
C or something like that.
There's line feeds, vertical tabs, all this other stuff that
We don't.
don't have to worry about that.
Unicode as a superset of ASCII, right?
I'll talk about this. Yeah. Hold your question. I got it. In fact, it's the next slide. So this is what it is. So based on these these bytes, you just look up the hex version, or if it's in decimal, look up the decimal. But typically it'll be in hex, and then you just map. Hey, hex 31 is the character 1. Hex 32 is the character 2. Hex 33 is the character 3, and there you go. All right. Simple table lookup. I want you guys to do this activity. Pick a snippet from 1 to 6 and decode that using, hopefully that's readable. Can you guys read that? Just for fun. And then this is just sort of a group activity. You'll need to get sort of 6 of you together to do it. So, if you got your pencil and paper. And this is your, write down your answer, because this is sort of I collect these sheets afterwards for attendance. That's how I'm taking attendance. So. And I forgot to bring scratch paper, unfortunately. Okay, so let's continue. Hopefully that gave you some practice decoding ASCII. So when you're reverse engineering your binaries, for example, and you see stuff like this showing up on the stack, for example, well, that's a string stored on the stack. Or maybe it's in a data section. You can pull apart the what the string actually is. And there are tools that look for this. So there's this strings utility in Unix. And all it's doing is looking for sequences of codes that are all printable. If every single one of these, I think it looks at 4 or 5 characters in a row. So if you do a strings on a binary, it's going to find all the places in that binary where you have 4 or 5 printable ASCII characters in a row, and then it's going to spit that out to the terminal. And then you can pull out symbols out of the binary.
So there was an add-on or command that you could use the object from command that was I think it was a -p or something like that that shows strings. Does it do that?
Similar. Everyone's got a different heuristic. Sometimes you want every 3 code points that are printable to output to the terminal. Sometimes people are like, no, I need actually more than that. I want like 4 or 5. So that's the idea. But it's a heuristic, right? Like you're scanning, you're treating the binary as a flat blob of bytes. And then you're looking for sequences of printable codes in a row.
I've seen binaries with like null characters between each character.
So bad guys know you're going to do this. So what they'll do is they'll interleave null bytes or non-printable bytes into their string. So it's not so easy. And now your initial binaries, like the first 2 binaries, you could have just done a strings on that binary and seen the password show up. But on subsequent ones, I've made it a little more difficult, hopefully, so that you're not just doing that. Okay, so the next thing we're going to talk about is data in memory. So I mentioned earlier that memory is organized as an array of bytes. So there's a blob of bytes. And we talked earlier about how the process abstraction, one of the key things that the operating system gives an application is this illusion that it owns the entire memory space. This is the entire memory space. This is the illusion that it's providing. Addresses from 0 all the way to all Fs, the process believes it can access and address. All right? And then, because this memory is organized as an array of bytes, every address specifies an 8-bit quantity. It's byte addressable, these architectures. And so a byte is either binary all zeros all the way up to binary all ones, or in decimal it goes from 0 to 255, or as you saw with hexadecimal it goes from 00 to FF. And then typically the address is basically an index into this array to find the data that you need. Okay. The other thing that every machine has is this notion of word size. And this is the nominal size of pointers on a system. So how big is the address? You know, how many bytes are in the address that you're specifying? It basically talks about what is your maximum addressable memory space. And that determines the address size, because you need a certain amount of address space in order to address every single byte. So with 32-bit x86, the word size was 32 bits. That's what gives us this 32, or 4 bytes. So a pointer in IA32 is a 4-byte quantity, and this allows you, 4 bytes allows you to address 4 gigabytes of memory. Now, we quickly surpassed the 4 gigabytes of memory on our motherboards, so eventually we needed more, and so that's where we transitioned to a 64-bit architecture. And with the 64-bit address, every word is now 8 bytes, and the pointer, so the size of the address, is now 8 bytes in the 64-bit architecture. And this gives us up to 18 petabytes of addressable memory. And of course, no system has 18 petabytes yet. So even though you get the illusion that you own all 18 petabytes, you actually have to allocate the memory that you want to use before you can actually address that memory. So, yeah. Okay, so one of the key issues when you have words in memory is how they're stored. And so typically when you have a pointer or an address stored in memory, the word itself is stored over contiguous byte locations. And moreover, the address of that word specifies the lowest address. So here you have, for example, an integer. And if this integer has an address of hex 4, then hex 4 is the lowest byte of that integer, and the rest of the bytes are stored from 4 to 7. So your word is the address of a word is always going to specify the lowest address. And then addresses of successive words differ by 4. So if you have a word here, the next word up is 4, because this is a 4-bit quantity. Or in 64-bit land, the word is 8 bytes, so it goes from 0 to 7, and then successive words are 8 bytes apart. Pretty straightforward. We have this issue where if you have a word, for example, this integer x, and this word is hex 01, 2, 3, 4, 5, 6, 7, how do you store this byte in memory? So if you assume the address of x is hex 100, so here is hex 100 here, how would you store 01, 2, 3, 4, 5, 6, 7? Do you store it by sticking the most significant byte in hex 100 and then go 2, 3, 4, 5, 6, 7? Or do you start with the least significant byte, the 6, 7, and then go up from there? So then 6, 7, 4, 5, 2, 3, 0, 1. How many of you would do the top? All right. Some people. How many of you would do the bottom? Okay, about half and half. Turns out there's no right way there's no right or wrong way. It says it doesn't say anything about you as a person either that you chose one way or the other. It's a different way of organizing memory, and either way, you'll see either way show up. So the folks who chose the first way, you're the internet folks, because that's the way the internet stores things. The folks who chose the second way are the x86 and ARM folks. You're the device folks, the end host folks, because those guys store it the opposite way. So the notion is called endian. The endianness of the system says if you have a word, how do you store that in memory? Do you store the least significant byte at the lowest address? Or you take the least significant byte and you store it at the high address? One or the other. The mnemonic that I would like you to remember is that for a little endian system, the least significant byte has the lowest address, or LLL. And then the opposite is big endian. Okay, so revisiting the example, variable x is at hex 100, has a 4-byte representation. Which is the least significant byte here? The 67. That's the smallest end when you're treating this as an integer. So for big endian, where would the 67 go? It'd be at 103 at the high end. And then you would store 4, 5, 2, 3, and then 01, which is the most significant byte, would get stored in the lowest address. And then little endian is the exact opposite. You would store the 6, 7, then the 4, 5, then the 2, 3, and the 01. Right? Now most of, like when you go hit a debugger, almost all the time you're going to get this. And then what do you do when you want to like communicate over the network? Well, there's these byte reordering functions in operating systems to switch it around. Transmit it the opposite way, right? Because that's the way the network wants it. So, all right. One day, there'll be a field of study called computer anthropology, which will go to all of these sort of like, why do we have this, that, or the other in a computing system? Because there's so many random, arbitrary things that people don't know why or how they came about. That's my, I surmise that, so we'll see. Okay, so how do you test the endianness? So one of the ways you can do it is by direct introspection via GDB. So here's your program. You have your integer, and you print it. What I'm going to do is go into a debugger, set a breakpoint, and then examine the byte at the address I. And then this will tell you, because this is the low byte that you're examining, whether or not it shows you 04 or 01 tells you exactly whether or not the endian is one or the other. So I'll show you that. I have my virtual machine up. Oops, I don't. All right, so here's the, All right, so here is the endian program. I compiled it. I run GDB on it. There's the program. I'll set a breakpoint at line 5. I'll run it. I hit that breakpoint, and then I can do an x/b of the address of I. And it shows me, let me do an x/bx. That's in decimal by default. So if I do x/bx, I say, show me the byte in hex of the address I. It gives me hex 4. And then if I do an x/bx again, it'll give me the next one up. 3, and then 2, and then 1. All right? So little endian.
So does that mean if there's trailing zeros, that it would just be put into the front or back, whether it will be endian?
Trailing zeros?
Like if you only use, half of your memory space.
So if you had 0304 instead, then yeah, let's see, on a little endian system, these two, the last 2 bytes would be 0000.
Yeah.
The high 2 bytes. Yeah. Yep. Okay, so let's talk about representing pointers. Pointers are just addresses, so there's nothing too fancy about them. They contain a reference to the data. And we saw earlier that their pointers can have any number of types. So here are 2 pointers, the character pointer CP and the integer pointer IP. One declares a pointer to a character, one pointer to an integer. So on x86-64, how many bytes is CP? Just yell it out. 8. 8 bytes because it's 64 bits. Divide 64 bits by the number of bits in a byte, which is 8. 64 divided by 8, so 8 bytes. On a 32-bit system, it's 4 bytes. Yeah. So this is 8 bytes. How many bytes is IP? Also 8. So yes, I tricked so many people on that on the exam. Well, I don't try and trick them, but like, what's the size of IP, CP? They're all 8. The size of a pointer is the word size, not the thing that it's pointing to.
Right.
So here's what gets everybody. They see the character and they're like, oh, that's a 1 byte quantity. But this is a character pointer that immediately means an address. All addresses are 8 bytes on a 64-bit system. So before I trick you on an exam, just remember that. That's probably going to show up, yeah.
That's why a lot of people, there's actually a really large and stupid argument about where you should place the asterisk. Some people want to place the asterisk on the variable name, some want to place it on the type name, and the biggest argument for placing it on the type name is so that it indicates that it's a char star, which automatically means it's that size.
Yep, but you'll see it in both, so definitely train yourself to notice both. So what he's saying is that in the declaration, you can either say car star CP, or you say car star CP. Equivalent. Equivalent declarations, you'll see both of them. So you need to train yourself.
I just heard somewhere that, like, if you have the star on the side of the char and not in the CP, if you have like a huge program in C, it might actually start bugging just because of that.
Okay.
I wasn't sure.
So when you are not obvious in the way you declare variables, and someone comes in and tries to read your code, and it's not obvious, this is where the bugs will get injected. And when I talked about the power of 10 rules, that's exactly what that's getting at. Is like when you start embedding multiple levels of indirection in your program, yeah, you might understand it, but the poor person who follows you, who tries to use your code, is not, and that's where all these errors will get injected. Yeah. All right. Okay, so pointers in memory. So here's some code. You have an integer b, it's negative 15 to 13. You have an integer pointer p that's holding the address of b. Suppose the addresses that hold b and p are these two ugly things. They're stored right next to each other on the stack, basically. So at D0 and maybe D8. Okay, D0 and D8. So at the end of main, write the value of each byte of P in order of its appearance in memory. So this is what it looks like. So here you have set P to be the address of B. And so P starts at D0, goes all the way up to D7. And then because this is a little endian system, then you will have the low byte of B at D0, and then all the way up to 07. Does that memory layout make sense to you? So you have the pointer P is going to be set to the address of B. And so the address of B is this. The address of P is this. So it is asking you what is the layout of P in memory. So here is the address of P at D0 all the way up to D7.
Okay, those are the addresses.
And then it got set to the address of B. And so it's going to store this quantity at that location. And because it's little endian, it's going to store it in a way that goes from the least significant byte of B all the way up to the most significant byte. So this is where you get D8, F8, FF, 07. Okay. Yes, at the address, at P, yeah, the address P.
So the address of the last 00 is 7F, FF, 8, D2, I mean D7?
D7, correct.
Okay.
Yeah.
So little endian sequences start with the least
Significant byte in the lowest address.
the largest.
Yeah, yeah. But get used to the little endian. Because pretty much that's the last time you'll ever see big endian in this class. It's done. So everything now is little endian from here on out. I just had to show you big endian because there are some cases that you'll come across. So, okay. Representing strings. So the string is represented by an array of characters, and it's terminated by a null character. So every string in C has all of these ASCII codes followed by a null byte. Now, they're encoded using this ASCII format, which is that 7-bit encoding we mentioned earlier. And because these are, you're storing characters 1 byte at a time, you don't have the endian issue that you had with a word-sized piece of data like the integer or the address. So what you do when you store a string is you store the very first character at the low address, and then you continue all the way to the end of the string, and then you follow it with the null. And this is why, so 31, hex 31 is the character 1, as we remember earlier, and then 38, 36, 35, 34 is 18,654, followed by a null. That's this number as a string, right? You can't use it as an integer, because the data type is a string. And you'll see on a little endian system or a big endian system, this string is stored exactly this way on both systems. Yes?
Is that because it doesn't know how big that string is going to be?
No, it's just because you're storing bytes at a time. You're not storing a multi-byte quantity in terms of a semantic whole quantity, which is an address.
Well, to evaluate it, if it was a reverse order, you'd have to point to the last character in memory and then work backwards.
And that, but yeah, you wouldn't. So if you had a big endian string, that would be an awful piece of code to write. Okay. So this is why text files are generally platform independent. You don't have to convert from one endian to another when you're transmitting text files. But there are different line termination characters between Windows and Unix. So that's the only conversion sheet. Okay, so as was referred to earlier, ASCII is only suitable for English text. So when we started to internationalize, application localization started to happen, then we're like, well, with 128 characters, I'm supposed to represent a language like Chinese? Are you kidding? There's I think it's like a normal Chinese person knows 30,000 glyphs. Like, how are you going to do that in a single byte? So this is why we started to do first 16-bit Unicode, but now we do have a 4-byte Unicode representation, specifically for these character sets in foreign languages that require all of these different codes for different kinds of glyphs. And so you'll see, initially C was developed without regard for any foreign language. And so everything in C is using ASCII. ASCII is the native representation of strings in C. When you get to something like Java or Python or some of these other higher level languages, they have gone over towards Unicode. Or in Python's case, in Python 3, they're like, a string is completely an abstract thing. It's only when you want to store it into a file or send it across the network that I'll force you to encode it. So now all these strings in Python force you to do a dot encode and force you to select, well, what do you want? ASCII? You want Unicode? You want EBCDIC? And so it's a pain in the neck, but we have to have that in order to support other character sets. Okay, so the default encoding for strings in Java is now the 16-bit Unicode, but it also supports the other character sets as well. Now, if you want all these other character sets in C, you have to find libraries to do that. It's not part of the standard C, as far as I can tell. Okay, the book has a program that will show you how to output. If you have variables like this declared, the book has this thing called show bytes, which allows you to figure out how these bytes are stored in memory. Bryant O'Halloran. What do you have? Oh yeah, this is the Bryant O'Halloran have this code. Oh, this is what the code is. And so I'll walk through this very quickly. They define this byte pointer. So what they want to do is they want to put a byte pointer at the address of I, the address of F, the address of IP, and the address of S. And they want to use this byte pointer and increment it by 1, and then dump whatever byte's there. And so structurally, you have an int float, an integer pointer, and a character pointer. But what this show bytes does is like, give me a byte pointer that's starting address, that's a byte pointer, and a length. And then for I from 0 to that length, I'm just going to print the 2 hex digits at that location, start of I. So this is what this routine does. It just spits out 1 byte at a time for a certain number of length bytes. And then you have show int, show float, and show pointer, which takes these addresses and passes the address as a byte pointer. It casts it as a byte pointer, and then the size of the quantity to dump out. And so here we have these 4 variables and a show int, show float, and show pointer, as well as show bytes directly on this memory location here. And then you can see for show int, you see the little endian, 04, 03, 02, 01. For the float, you see 9A, 99, 1245. This is the IEEE floating point format, which we'll get to in the second half of this class. And then here's your pointer IP. It's 7FFC63616128. That's the address. And then you see show bytes directly at this address here gives you A, B, C, D, E, F. Okay. So yeah, you can use that program to poke around.
Is there a reason why we have unsigned char? I thought char itself was an unsigned type.
Aha! Char is signed by default, unless you explicitly say unsigned. I'll get to that.
Okay.
I'll get to that, yeah. Okay. In fact, it's right here.
Yes!
So, finally, we're going to get to representing integers. So, there are support for multiple size integers in C and in x86. You have the character, the short, the integer, and the long, and it's either 1 byte, 2 bytes, 4 bytes, or 8 bytes. Now, there are 2 kinds. For each one of these data types, there are 2 kinds. You're either talking about an unsigned integer or a signed integer. So you have signed characters and unsigned characters. By default, everything is signed. If you give me a car, that by default is signed. So by itself, car, short, int, and long are signed. Yeah.
So I don't understand when you say a car is signed, they represent the ASCII value, right?
That's true. It can do both.
Maybe the mapping could be
Yes.
signed to unsigned. Is that what it means?
As you interpret that byte, you can interpret it as an ASCII character. If you do I should be more precise. The data type itself doesn't have the semantic. That particular data type doesn't have to hold only ASCII characters. It's used as this. So it's used to specify an 8-byte quantity. The fact that we're using char is unfortunate because that implies ASCII only. But this is actually any 8-bit quantity from 0 to 255. So you saw in ASCII, it was 0 to 127. It's unfortunate that this got named char. It got its name because most of the time it's ASCII. But this is independent of that. I know that's really confusing.
So when they say car, they just mean
8 bits.
integer.
An 8-bit integer, yeah.
Especially now.
Unfortunately, if you want it to be. So, like, if you pass a car to printf and then use the %C, that says, okay, give me the ASCII for that. If you pass it using %X, that means give me the hex code for that. Don't give me the ASCII. So this is why the car, it's just specifying the 8-bit quantity, and you can still put the semantic on top of that to say, give me the ASCII, or just give me the raw, hex value. Yeah.
Is for an integer, the highest value is
For an 8-bit number, it goes from 0 to 255 if it's unsigned. Yeah, 2 to the 8 minus 1 is basically what you're 2 to the 8 is basically what you're getting. Yeah.
But sorry, back to my earlier question. But from signed to unsigned, it's still not changing that ASCII table, right? I mean, 00 is null.
Yeah, these are just bit patterns. Okay, yeah. How you interpret signed versus unsigned is another thing. If you want to interpret it as an integer, so this is, if I take this car and I want to interpret it as an integer, then this is what unsigned and signed does.
Okay.
If I take that car and I want to interpret it as ASCII, there's only one way to interpret that as ASCII. Yeah. So that's where the difference. Yeah, that can be really confusing.
Does C support extended ASCII on 127? Or does it?
It would be done via a library. And you have to enter it.
And if you were to like print def 129 or something,
It would give you garbage. But yeah. Okay. Is that clear for everybody? Because this is a subtle thing where character doesn't really specify ASCII. I mean, the name implies ASCII, but in this context, it can be used either to store an integer, or it could be used to store an ASCII sort of character code that you would want to print the character for. Based on the context of you using this character, how you sort of output it, you could get one or the other.
This is just that computer anthropology thing. We're like, when we used to have to save so much space, like let's represent the number 20 with the character.
Yeah, and you'll find in other modern languages, for example, in Rust, I think it's a U8 int, right? An unsigned 8 integer. It's like, oh yeah, that's a great, or maybe byte. Like if they would have just said byte, then this confusion wouldn't have happened. And then, interpret my byte as either ASCII or leave it as an integer. That would be easier. Yeah.
So what was the point of doing the unsigned car pointer then?
Um,
Pointer if you're using printf and specifying what you want.
So you could have gotten away without doing an unsigned car pointer. Yes. This could have been just a car pointer. Because you're printing this.
Because you're identifying the type you want to print.
Yeah, actually, later on in this talk, we'll talk about why it actually does matter, because there's this thing in C. This is why C, it's like, there's this thing called integer promotion. And I will talk about all the bugs that integer promotion causes. So, yeah, I'm going to show you all the works in C, and then hopefully at the end of this class, we'll talk about a modern way of doing things that avoids this, yes.
Is the car specifying size?
Yeah, it's specifying size, yes.
Integer promotions where you go from something with little range to from something bigger range to something
Yeah,
bigger range.
and it's automatic. It's automatic in C. So, yeah, it's enough to. I have some of these code examples, and you'd be like, oh my gosh, I have to remember that. Yeah.
Is promotion only going from a larger range to smaller range or smaller range?
That's truncation. We'll talk about truncation
Okay.
also. So,
Promotion
and if we talk about too many of these things, I won't get the floating point. So hopefully, but I am gonna address that. Let me know if I don't. I promise I won't skip that slide if I come to it.
Promotion meant both directions or just one of them?
Promotion is one direction.
Right.
Truncation is the other. Okay. So if you do declare a char and want to use it as an integer, then there are two ways to use that as an integer. One is the unsigned and one is the signed. And the only difference is how the bits are interpreted. The actual representation is the same. You're just telling the compiler that's a signed integer versus that's an unsigned integer. And the compiler is going to use different instructions when it processes those bytes, knowing the type. Because the compiler is sitting there, it knows all the opcodes in the CPU, and it knows how you declared signed or unsigned bytes or cars or ints or whatever. It's going to generate the opcodes based on what you've told it, and that's why you have to declare these things. Yeah.
So we'll assign car output like or will output.
When you print it out as a decimal or you print it out as a hex thing, it'll just give you a number. If you say print it out as a character, then it'll give you the ASCII. Yeah. Okay. Yeah.
Question. I mean, because this relates us to the program practically you're doing.
Yeah.
We have to use this the scanf to convert. Like when you're extracting the value from the chart, you have to use the scanf.
So scanf is beautiful in that it gives you any string. So all your input is a string, right? But your program is like, I want to treat that string as if it got converted into bits. Like you get a hexadecimal string, and you're like, well, how am I going to get that into bits? Well, scanf in particular says, yeah, treat that as hexadecimal codes, and then just scan that into an actual integer, integer value. So did that answer your question? That makes sense. Okay.
Absolutely.
All right. So here's an example. Unsigned int I. If you do a printf %u says treat this variable as an unsigned integer, and then what this will do is it'll encode I as an integer from 0 all the way to 2 to the 32 because it's 32 bits. The integer is 4 bytes or 32 bits. So that exponent is 32, 2 to the 32 minus 1, and this goes from 0 to 4 billion. So that's the range of an unsigned int. If you just have a regular integer I, well, this is a signed format. So this gives you the 2's complement. It's called 2's complement, and it's a very specific encoding of the bits. This will give you negative 2 to the 31st to 2 to the 31st minus 1. So it takes your range and it shifts it to straddle the origin, so you can get both the negative numbers and the positive numbers. But the range hasn't changed. It's still 4 billion, but now you can get negative 2 billion to positive 2 billion instead. So that's what the signed integer representation is going to give you. Okay. I should say that this is not common in programming languages. In fact, C is one of the only languages that has this unsigned versus signed integer. In Java, all integers are signed. And in JavaScript, every single number is a float. They don't even have integers in JavaScript. So different languages, when you learn a language, you have to look at the data types first. What are the data types this thing supports? Because if you don't look at them, you're going to be finding nonsense stuff coming out of your code that you're not going to understand. So, okay, so how does this work? And this is very scary, but I'll explain it. How do you go from a byte to its unsigned value? That's what BTU means. Given some sort of number x, well, this is the formula we saw last class. You take the sum of all the bit positions, the values of the bit positions multiplied by the bit position value itself. So 2 to the I times what that bit position has, either a 0 or 1. You add them all up, and that's your decimal, or your value for x. Okay? What I'm going to do is I'm going to pull out the most significant bit. So x of w minus 1. So this is a w bit integer. And it goes from bit 0 to bit w minus 1. So that's just the sum of all the coefficients multiplied their value positions. You pull out the most significant bit. And this is xw minus 1 times 2 to the w minus 1. And this is the rest. The signed representation takes this bit and puts a negative sign on it. That most significant bit, rather than being a positive large number, is now a negative large number. That's the difference. That's the only difference between an unsigned representation versus a signed representation. Okay, so here's the concrete example. Here's your unsigned car. These are your 8 bit positions, 128, 64, 32, 16, 8, 4, 2, 1. And you flip the sign of the most significant bit. That gives you your signed character. Yeah.
So the range of version from 0 to
255, yep.
ladders,
7. Yep. In fact, I think I might have it in the next slide. But yep, it's good. It's better that you come up with it first before seeing it on the slide. Yeah, and here is a 16-bit example. You go from 1 all the way up to 32,768, and then for the unsigned short, so the unsigned short is 2 bytes. So this is 16 bits or 2 bytes. So that goes to 32,000, and then you flip that sign on that most significant bit to get the signed representation. Yeah. This is in decimal. Yeah, these positions are in decimal. So this goes from 0 to 65,535, and then if it's short, it goes from negative 32,768 to positive 32,768. All right? Yeah. Yeah, but I won't give you that one. Yes, that's correct.
really hard to overflow.
Yeah, very easy to overflow this, very easy to overflow this. If you have mix and match these unsigned and the characters, you've probably blown up your program as well. So lots of issues here just in our data types. And this is where not having solid data types really messes up the programming language, which is too bad because C is everywhere. So here is an example. I have two short ints. So these are signed data types. And you see, as before, these are the bit values, all the way to negative 32,768. Here is positive 15,213. It's 8,000 plus 4,000, 2,500, all the way down. And here is negative 15,213. And if you look at it, how are they similar or how are they different? Look for a pattern, yeah. If you add these two together, you'll get 0 with a 1 carry, and then this is 0 with a 1 carry, and etc. all the way down here. Yeah, you'll get 0. So here's a good thing. When you do subtraction, you can implement it as addition in this format, right? If I do 15,213 minus 15,213, rather than have a subtraction unit, I just need to represent negative 15,213 and then send it to the adder. This is why this data format is the way it is. This is why we don't have a sign bit followed by the magnitude, as you are typically, you're familiar with in math class. This is why that most significant bit position is negative 32,768. And this allows you to use the same adder to do subtraction. Yeah.
Well, in this format, you're not having to have a signed 0, so you're gaining one range.
You save one, but yeah, that is also correct. If you encoded the sign separate from the actual number, then you have positive 0 and negative 0, and that tends to make programs unhappy.
And
right?
there are languages that have that. And it's pretty simple.
Yeah, in fact, we'll talk about, there is a positive and negative floating point 0 in but the other thing I want you to notice is that these are almost the bitwise complement of each other, except for this least significant bit is the same.
That means you can just flip everything and add 1.
Yeah, so this means if you want to go from positive 15,213 to negative, you flip all the bits and then you add 1 at the very end. Yeah. So this one is an example because you only have to do, it doesn't carry over, but like that's basically it. So that's why this number representation is pretty universal for integers on most processors. Okay, so we noticed the pattern. Okay, so here's an exercise for you to practice. Write -3, -4, and -5 in 2's complement format for a bit width of 4, and I've already conveniently listed your values. So I'll give you a minute for that. Do it directly rather than you could do a bit. You could represent 3 and then do that trick. But I think it's better if you just do it bitwise. Start with this bit's got to be 1, and then you figure out what to add to it to get to any of those.
Do you want to see the summation?
I'll tell you. So -3. I'll start with -8, and then what do I need to add to -8 to get to -3?
3.
So yeah, you could do that. Okay, you could do it your way too. You start with you could start with 3, which is 011, and then flip all the bits.
Yeah.
And then add 1. Okay, that's fine too. But I'd prefer you to see how these value positions work to generate that formula, because eventually that's your formula, your rote formula. But how do these bit positions work to get you that negative number? That's what this exercise is helping you do. Yeah. The number itself has 4 bits. So for show 4 bits for -3, and then what is -4's? Yeah, so there'll be 3 rows here for the bit patterns of each of those numbers.
So that's
We're
B, C,
assuming we're
D.
working with a 4-bit.
Yes, so that's when I say W is equal to 4, that's the bit width of these numbers. Yeah.
So it's B, C, D. Or, sorry. B, C.
Hold off. I want people to sort of.
It's 4, right?
Okay. So for -3,
But you have 8.
you start out with -8, and then you have to add until you get to -3. So you add 5, so this is 101. This gives you -3. For -4, you start with the -8, and then you add 4 to it to get -4, and then the rest could be 0. -5, again, you start with the -8. If you add 4 to it, you've gone too far, so this is a 0. If you add 2 and then 1, then you can get to -5. Questions? Can I continue? So if you map out all of the 4-bit patterns, you'll get this. You'll get the all zeros to 0, 1, 1, 1. Gives you your number 0 to 7. If you go from this to 1, 0, 0, 0, in an unsigned format, this is +8. But in a signed format, it's -8. That most significant bit got flipped. And then you go from -8 all the way down to -1, which is all ones in a 2's complement format. This takes some getting used to, seeing this. And I'll show you some more pictures of these ranges to hopefully help you get acclimated to this. All right, so numeric ranges. For a 16-bit signed number, so W is 16 now, write the greatest positive value and the least negative value in hexadecimal, and just do it in hexadecimal first, and then I'll talk about decimal. And then what does -1 look like in this format? So I'll let you 16-bit format. This is something you might want to collaborate with if you talk about this one. This is not as simple as the previous one. So what are the first thing you have to do is, what are the bit patterns, and what bits do I need to set to get all of my bits to be the largest, and what are the bit patterns that I need to set to get the most negative number out of it? So this is think about that first, and then write those bit patterns out, and then convert it to hex.
Is this part of the thing you collect at the end of class?
Yes, but I'm not grading for correctness.
No,
Yeah.
just one question.
Oh yeah, write it down on a sheet of paper that you can hand me with your name on it, or write your name on something and hand it to me.
But it could be 0.
So I'm going to use this slide to give you the answer. The largest positive number, all you have to do is set these bits for these positive locations all to 1, and then this has to be a 0. So 0, 1, 1, 1, 1, 1, 1, all the way to the end. If you represent this in hexadecimal, this is an F at the end, another F, and then this is 0, 1, 1, 1, that's a 7. So the largest positive number is hex 7, F, F, F. Turns out that's 32,767 if you do this. Basically this minus 1, 32,768 minus 1. The most negative number in this representation, it has this bit set, and then all of these are 0, right? So, and its value is negative 32,768. In hexadecimal, when this bit is set and all of these are 0, well, this puts a 0 here, a 0 here, a 0 here, and then this turns into 1, 0, 0, 0, so this is hex 8,000. All right, and then -1 is this, it has to be negative, so this bit has to be 1, and this is followed by all of these being set to 1, because negative 32,768 plus 32,767 is where you get your -1. So all the bits 1 is your -1. So that's what I have here. as the answer. Questions about this number format? Yeah.
So hex represents 2 binary numbers for every one. And that represents
2 hex digits for every byte.
for every byte.
Yeah. Wait, was that your question?
So SF represents 1 byte.
Yes.
It would be binary. 2 bytes.
4 1 or 8 ones. Sorry. So every one of these represents. This is 4 binary bits that are 1, and another 4. So this means 8 bits that are all 1s. Yeah. This can get confusing. A hex digit is not a byte. You need 2 hex digits to get you that byte. Which is 8 bits. Yeah. So this is why I'm spending so much time on this, because if you don't understand this, I mean, this is sort of the bedrock, right, of your data representation. In order to get to the higher level sort of representations, we have to have the basics here.
It's great. It's great. Never mind, I figured it out. I was wondering where the 1 came from for the choose complement, because you have to add 1 to get the negative of the same. But then the greatest negative is 1 more than the greatest positive.
Oh.
So
And I have an extra F here.
Okay, that's what I thought.
Sorry. Man, I've been using these slides for a while. No one's caught that. I think they're just too glazed over at this point to know. Yeah, that's it. Okay, so we looked at this before. Well, what are these ranges? It definitely helps you to know the ranges of your data types. So, for example, the 8-bit range, if it's unsigned, goes from 0 to 255. If it's signed, it goes from negative 128 to 127. Likewise, for 16-bit, you have the 32,000 to negative 32,000, and then 4 billion for 32-bit. And then if you're in the 64-bit range, you got like lots. I don't even know how to say this number, but big is what I would call it, yes.
Do we have to memorize like the values? I mean, some of it's pretty intuitive, but like we have to like know the 32-bit sizes and 64 sizes for a test.
No.
Okay.
Yes. But you should definitely know as you're programming, this is 4 billion. So if you're modeling a large number, yeah, you should be like, oh, I'm getting towards the billion range. That's danger. And I got some examples of this where, yeah.
Like the YouTube thing Anthony last year. The view count.
Oh, really? Did it wrap around?
That,
Oh yeah, with the
It goes style.
yeah.
Oh, it wrapped around?
yeah, wrapped around.
Oh, sweet.
That's kind of cool, actually.
They had to change that.
Okay, so casting. So sometimes you'll have a mixture of signed and unsigned numbers in your program. And this will happen more often than not. What are the rules for casting? Well, when you go from integer to integer, in particular from signed to unsigned, the only thing that changes is the way you interpret the bits, right? So that most significant bit, that interpretation as being either positive or negative, that's the only thing that changes when you cast from one data type to the other. The bits themselves don't change. They're the same. So, for example, if you have this signed integer, 15,213, you cast it to an unsigned, that most significant bit is 0, so nothing changes, right? So that's why unsigned, this is still going to give you 15,213. If you have this negative 15,213, it's a signed integer, and you cast this thing to be unsigned, then this is going to turn into 50,323. It's going to take instead of negative 32,000, it's going to add positive 32,000 to this number, and then you get this large swing in the value of that integer. Okay, so that's a picture of what it does. I'm going to show you an example using a 4-bit number sequence. So on the right is your unsigned thing, and the bit pattern is exactly the same for both the signed and the unsigned. And here it goes from 0 to 15, all zeros to all ones. And then when you interpret these bits as negative 8, 4, 2, 1, if you look at this, the top is the same, right? The most significant bit is 0. There's no change in interpretation. As soon as you get to this most significant bit being set, then what you're doing is that instead of making this -8, you're basically adding 16 to each one of these numbers to get the top end, right? So this is visually what you're doing to your number range when you're casting from signed to unsigned, or like signed to unsigned and vice versa. You're adding or subtracting twice the most significant bit value. Here's another picture, number line. So here is your unsigned region. It goes from 0 to unsigned max. When you cast this to sign, you're going to take the top range with the most significant bit set, and you're going to move it all the way down to the bottom. You're going to take this twice of this range, and then move it down. So that's what you're doing to your number line. All right. Okay, so what happens when you have signed numbers and you compare them to unsigned numbers? What do you think should happen? Should the compiler say, "What the heck are you doing?" and throw you an error?
That would be ideal.
That would be ideal. In fact, if you're in this department, you'll end up taking a compiler's course taught by a functional programming, an expert in functional programming with strong type systems. What do they mean by strong type systems? Strong type systems are like the ones that say you're mixing your signed and your unsigned numbers. I'm not going to compile. C is not strongly typed. C is like, I'm going to guess. And a language like PHP is PHP is classic. PHP is like, I don't know what you're doing there. I'm going to guess. And hopefully I guess the way you think I'm going to work. That's basically PHP, and that's what C is a little bit.
Except C is consistent in their guessing, and PHP is not.
Yeah, well, PHP is developed by multiple people, and so different people have different ways of doing things, and it's not consistent. C was developed by a small number of the Bible. At least it's in there, and then they'll tell you, hey, you know what? This is undefined behavior, implementation specific, or these sorts of things. There's a standard that's been documented. So, but yeah, this is the difference between something that's loosely typed and is doing all these type conversions and these sorts of things with something that says, compile error, fix this problem, give me something more, or hey, maybe you had an error in there. So okay, so there's that. So in C, when you have constants, so first, when you have numeric constants in your program, by definition, by the standard, these are treated as signed numbers. So every literal is treated as a signed number. If you want a specific unsigned constant, then you have to put a U at the very end of that number, and it says everything is unsigned. Now, you can explicitly cast between the signed and the unsigned numbers. So if you have two signed numbers, signed integers, and two unsigned integers, then you can go back and forth by saying, take this unsigned integer and cast it into a signed integer. And all that's doing is reinterpreting the bits. Or vice versa. Take a signed integer, say this is now unsigned, and that most significant bit changes. If you do something like this, tx is equal to ux, it will implicitly cast the unsigned to a signed. So this is actually redundant. You don't necessarily have to include it. Some compilers will complain if you do this without putting an actual cast there. Because they're like, you need to intentionally say you're going to convert this in order for me to compile. So that's okay. So when you have a mixture of expressions of signed and unsigned, the C rule is that if you have unsigned and signed numbers in an expression, the signed value is implicitly cast to an unsigned value. Automatically and implicitly cast to an unsigned number, and then you do that comparison unsigned. Okay? That's the rule, because remember this rule, because we're going to start evaluating these things in terms of is this less than, greater than, or this, that, and the other. Okay, so we'll do the first two examples. If you have 0 and you compare this to 0 unsigned, well, this evaluation, because you've mixed them, this is going to be unsigned, and of course, they're equal, because 0 is equal in the same bit pattern in either interpretation. If you have -1 and you compare it to 0, well, these are two signed integers, so the relation is less than, right? Signed number. If you have -1 and you compare it to 0 unsigned, what is the evaluation going to be? The kind of evaluation is it's unsigned, and the relation is greater than. Well, that sucks. -1 is greater than 0. Turns out, what's happening is you're going to cast this, and you recall -1 is all ones, right? Especially for a short, it's all ones. If you interpret that as an unsigned value, that's a large number. And of course that large number is bigger than 0. But of course, if you have an unsigned quantity, and it's not going to be as obvious as this, where your 0 is, you got a constant, 0u, you could be just using a regular data type, an unsigned data type, like maybe a size token, or even a time token. In your first program, you use time t, that's unsigned. If you compare that to a signed number, guess what? That thing is going to be an unsigned comparison. Fortunately, you're not going to compare to, I don't know, if some of you have seen these crazy inequalities, that's what's going on. All right, so the next one, you have this 2 billion to -2 billion. What is the kind of evaluation? Signed. And then this will give you what you expect. What about if you make this unsigned and you compare it to that? It's going to be unsigned, and it's going to be the wrong side. This is just one off. This is going to be one off of the other one. This is all the low bits set, except for the last bit. And then this is the most significant bit set with zeros all the way at the bottom. So this actually is one more. Like when you turn this into an unsigned number, it's exactly one more than this guy. Yeah, it's like a bit complement is basically what that is. Yeah. So that's sort of strange. Am I running out of time?
No. Okay. It's like you got 30 seconds.
Yeah, it looks like I'm not going to get the floating point. Right. So I'll get the floating point. Wait, today's Tuesday. Oh, I'll just have to do it Thursday. I'll give you the weekend at least. I gotta. Yeah, I think that'll be fine. I'll just cover the floating point next time. So -1 compared to -2. So this is greater than. What about unsigned -1 to -2? It's unsigned.
-2 is going to be bigger, so it's going to be the opposite side. Oh,
yeah, -1. So -1 is all ones. -2 is mostly ones.
Yeah.
Except for that last bit. So again, this is going to be greater than. This is fine. This is what we expect, right? Yeah. All right. We're good. Well, you see, it's switching, right?
Some are good.
Yeah. I'll skip the other two, but it's similar, right? So again, this is something you just have to remember as part of this system. I have more stuff for you to remember, though. So this particular cast is very insidious. If you look around at C code, a lot of them have this kind of error where the signed and the unsigned are implicitly being casted and compared, and you're blowing up programs because of this. So here's a loop. Unsigned integer I is a counter, and you have an array of integers, and you're going to start towards the top of this array until this counter is greater than, you keep doing this loop as the counter is greater than 0, and then you subtract 1. And what you're doing is you're going to add the element that's your current element to, you're going to add the one after it to the current element all the way down. So spot the bug.
It's kind of sick. It's going to wrap around the engine.
Yeah, why would it wrap around?
Well, because when you're going from an unsigned to, you keep going down, it's just going to wrap all the way around because you got that extra bit for the unsigned. That's storing information.
Say this was set to 5. So how would it keep on going?
We go 4, 3, 2, 1, 0, and then it would wrap all the way around to negative 2, 1.
It would wrap all the way around. You were close.
To be,
It would wrap all the way around to 4 billion.
Yeah.
oh yeah. You would
So here's the bug.
Oh, because lesser equal.
Is this ever false?
No.
No, you have said unsigned int, and then your stopping condition on this loop is greater than or equal to 0. By definition, an unsigned int is greater than or equal to 0. Yeah. Huh. All right.
Why does it go forever?
Infinite loop, yeah. So this is the halting problem. Yeah.
It's a good practice if you want like an example.
If you want to obfuscate an infinite loop and inject it in someone else's program,
Yes.
that would be cruel. Hopefully they know how to use a debugger. Figure out that this is the loop. Okay, so what about the next one? Where did this go wrong? It's similar. Yeah.
Size of does not give you the positive, it gives you the full range. So you can go from negative 2 billion to positive 4 billion. So the size of it means you can go 4 billion is range. So it's just going to keep going all the way through, and it's never going to give you a negative number.
Yes. So the key here is that the return value, so if you look at the definitions for size of, when would you ever have a negative size? Never.
Right.
So they're like, oh, well, I'll make this an unsigned int, right? So size of is an unsigned number, an unsigned integer. And then when you mix this delta and you do this subtraction is done as an unsigned subtraction. Moreover, this comparison is now an unsigned comparison. And so because you have used the return value of a standard C call, and that return value is a unsigned number, this whole thing is unsigned. And so you could be like, well, this is a signed integer here that I declared. This should actually let me know. It doesn't let you know.
Yeah.
Right? You see how subtle that is? That's really hard. That's hard. And you wonder, so when someone talks about how C generates unsafe programs, you think about these things because this is very, very hard to get your head around. Yes. For this one, you need to rejigger your for loop to take into account, this would be great if it was I greater than equal to delta or something like that, or something that stays in the positive range. It doesn't check for negative range. Yeah.
Couldn't you just cast the I into an unsigned int and then make sure that your comparison with 0 is an unsigned int?
If you cast this to unsigned, you still have to take care of the fact that this.
That's what I said. And
Yeah.
then 0 to an unsigned as well.
No, because this would always be true either way. So you
Well,
would.
because then it would be equal to, and then you start up with the big one.
Yeah. So yeah, it's not easy to fix this thing either, is it? You have to really think about it. So, all right, that's never false, regardless of the casting that you do.
Never.
Okay, so here's a potential fix. I is less than to count, so you're not actually running into the negative, like assuming something to be negative that will never be negative. Yeah.
Could you have recast delta as signed int?
You could have. But remember when we talked about readable code and trying to figure out, that makes it hard because when you write that code in there, I don't think a lot of people are going to know why you did that. That would throw me for a loop unless I knew something like this, like you do. So.
You definitely want to comment.
Yeah, you would probably. Yeah, this is to take care of the fact that C is got issues that aren't going to be fixed anytime soon. All right, so there's a potential fix. All right. Okay. Another thing with C is that when you go from a small integer size, like a car or a short, to a larger integer size, like an int or a long, the way this gets converted is you take the most significant bit and use sign extend. And that just allows things to work out in 2's complement so that you can get the exact same number in multiple size formats. So that is basically the heuristic that you need to know. And it works like this. You see 15,213, and you want to go from a short into a regular int, which is 4 bytes. You take the most significant bit, which is 0, and you sign extend it all the way. If it's negative 15,213, you take the most significant bit and you copy it all the way out to the end, and that will give you negative 15,213. Yeah, and the way this works with the number system is, you'll see why this has to be the case. All right. When you do this assignment, IY is equal to Y, where Y is the short and IY is the integer, C will automatically convert from the smaller to the larger, and then it will automatically do the sign extension. Basically, the compiler will. The compiler will see this, and it'll generate the x86 instruction to do sign extension from byte to word, or from word to long word, etc. Okay, so given this, calculate the value of negative 5. Well, if you remember what you had from negative 5 on the previous slide, start with that, and then calculate the hex value for w is equal to 8 for negative 5 and for 16. I'll give you a minute for this.
Yeah.
Yeah.
Does the sign extension thing still happen with unsigned?
It does not. Yes.
So we put zeros at
Well, yeah, it would null out the top, right? So yeah, if you had, for example, a car that was 128,
right.
that most, and you cast that to an unsigned car, 128, and you cast that to an unsigned int, all zeros at the end, and you get 128, which is good, which is what you want.
Yeah, it's just gonna be f in front of it. So
Yeah.
Okay. Oh, I don't have the answers on here. All right, I got a pen though. So negative 8, 4, 2, 1. This makes this 1, 0, 1, 1. And this is hex B. The hex value for negative 5, well, you just sign extend out to 8 bits. So this would be 1, 1, 1, 1, 1, 0, 1, 1. So this is negative 128 plus 64 plus 32 plus 16 plus 8, 4, 2, 1. And if you do this math, you'll get that this is also negative 5, which is FB. And then the same thing for the bottom one. You're going to just put 8 more ones off to the left here, and this is going to be yeah, I'm not gonna write all those bits out there. All right. You guys done with this? Can I go to the next one? This is on the screencast, so. Okay, so what should the output of this code be? Here you've got a character, a signed character, C, hex FF. And you say, hey, I want to treat this as an unsigned integer, so I'm going to set I'm going to explicitly cast this to an unsigned integer, right, this character C, and then I do a printf, interpreting this I as an unsigned integer. What's my output going to be?
Negative 1. That would be the biggest number.
Biggest number represented by a char, an unsigned char, is 255.
So yes.
255.
yeah.
How many people like 255 as an answer? Okay, so you can compile this, and you can print it out, and you don't get 255. You get 4 billion.
Which is the int, right?
Yeah. Well, this is terrible, right? Like, I would look at this and be like, oh yeah, that's 255. What happens here is that integers of smaller types, so the characters in the shorts, are automatically promoted before they're evaluated. So where did we go wrong here? When you take this character C and you use it in this expression, it's going to promote this character to an integer first, and then it's going to do the cast. You see how that's problematic in C? That's called integer promotion, and this is a source of all sorts of bugs in C. And this is why I'm covering it here, because until I show you all of these warts, you won't be motivated into finding a different language. So yeah, maybe your life as a C programmer won't be all roses, but if you see this and understand why you might choose a different language, here's one right here. This integer promotion issue. And it's very subtle, not obvious, but you run this program and you don't get what the programmer is expecting you to get. That's the big problem. If that programming language makes it easy to code up errors like this, get a new language. Or become an uber expert at this, and then maybe someone will hire you and pay you a lot of money because you actually know how to program C properly. But this is one of those things that you have to know. You just have to know this rule. All right.
I think a couple of rockets have blown away because of errors like that.
Yeah, I got the rocket example later on. Yeah, but that was a different kind of error. That was casting a floating point. I got that in the floating point slides of like $4 billion going up in flames or something like that out of a integer casting. Yeah.
Someone got fired.
I don't know. This might have been before GitHub, before repositories. So yeah, there might not have been a commit log that showed that that telltale code that got committed to the repository. Okay, so then what should the output of this program be? You have an unsigned car and a signed car. You print out their hex representations A and B, and then if you say is A equal to B, same or not same. What do you think first gets printed out here? What gets printed out for A? Print me the hexadecimal representation of car A. You think FB? Okay. And then this would be the same? This is the this is the unsigned FB, FB, and then these should be the same, right? If they're both FB.
No, they're not.
Yeah. So you compile this program, and look, it sign extended the darn thing. Like, what did it do? Well, printf says, oh, you got me a character here. I'm going to promote you to a integer first. So it takes the signed integer A, gets you a signed integer, signed car A, gives you a signed integer A, and then says, interpret that in its hexadecimal format.
Does it promote every?
Yeah, that's my question.
Yes.
Okay, so it's not just when you're assigning it to an int. It's always. It's just always.
Yeah. So yeah, this is sort of nutty, right? Not same. So you can lose many hours in the programming lab trying to get your head around the fact that this is happening. Yeah.
That first printf statement promoted the A. That's what happened.
Yeah. Oh, and this one too. This will promote it also, right?
So both of them will.
Both of them, yeah. The expression, any expression, it'll promote the thing.
I mean, so there's no way that it'll ever not be.
Yeah, no way it'll ever not be promoted.
Always, like if I'm ever using it in anything, I'm sending it to another function, I'm printing it, it'll always.
Yep.
Okay.
So this means like if you have that most significant bit set, yeah, expect that to get sign extended before you cast it. Yeah.
Does that mean it's only longs? Is that
Not long, but normal size.
Always use longs.
it's
You could, yeah, if you have a lot of space. Yeah, well, but if you're in an Internet of Things device, probably not a 64-bit thing. Still programming in C, because C, one of the nice things about C, it doesn't need an interpreter. It doesn't need a whole operating environment to run, so almost all of these IoT devices are C. And then what do you do? Like, I can't make everything a long. I have to, the minimum thing is probably an int. I'll still have some issues. Yeah.
I still don't get why the conditional A equals B promotion. If they just promoted to unsigned, isn't that what you were saying?
It does the promotion before it does the, hey, this is an unsigned comparison. So it's the ordering. So you would expect maybe the unsigned thing first and then the comparison, but in this it's going to, or then the promotion. But in this it's going to promote A, or no, yeah, it's going to promote A to this, and then say, oh, this comparison needs to be done as an unsigned comparison, and of course they're already different. So then that blows the thing up.
So is it promoting B too, or just not seeing the leading zeros?
It's promoting B as well, and you're not seeing the leading zeros.
That's what was confusing.
Yeah. Here we go. What does this print out? Character C, 128, unsigned int UC, so unsigned integer, and then I say UC is the unsigned int cast of C. Do you believe the same shenanigans are going to happen? Just raise your hand. Same shenanigans? Basically. So this is now primed your pattern recognizer to recognize that, yeah, it's going to sign extend. This is the most significant bit of that character set. And it gets promoted, and then it gets cast. So it gets promoted, all those ones. And then when you print it, of course, it's going to print as an unsigned, and it's going to print you 4 billion, which is not what you would expect when you write that program. You're like, that should be 128, right? Yeah. All right.
So is it because all of our mathematical operators are built originally for ints?
Part of it was the progression of going from an 8-bit system to a 16-bit system to a 32-bit system, and not being too lazy to force a change in how these things are done. You want that old program to be automatically promoting to the higher bit width. So yeah, it's not like it's not nonsense when you look at the context of the history. This is why computer anthropology is going to be a thing, because eventually you need that to reason about all this stuff. And that's basically what it is, right? You start with an 8-bit system, you want to go to the 16. Well, I got to promote my numbers to 16 bits, and it would be nice if the language just did that for me, because I'm too lazy to just try and convert. And this happens all the time with x86, with C, with any programming language. You don't want to junk all of the code that came before it, so you end up doing these sorts of things.
So is it possible to upgrade the language?
Yeah, so for example, Python's like, there's all this stuff that we don't want in Python anymore. So in 2020 or 2026, Python 2, junk. So any of you want to learn Python, start with Python 3. Because there's a reason why they got rid of a bunch of stuff. So you would use that. And any language has this.
Seems like it would have been more.
Python 2's got much more support for libraries and this, that, and the other. So that's why
massive
people
and
stick it.
change. The real reason between Python 2 is that all distributions still ship it. So like everyone runs Ubuntu and all those other light distributions that don't update a package for 10 years or whatever. Python 2.
I run Ubuntu. Yeah, I'm not lead enough to run the Arch thing, which I think a lot of you cool kids are running. I'm old school. I like moving slow. Okay, so those are toy examples. Now I'm going to give you real security bugs. Like this stuff has broken internet service. And I'm just going to give you a flavor of these things. And the slides are there if you want to try and reason about them after class, which, I don't know how much time I have.
20 minutes.
Oh, I got 10 minutes. I'll at least do the simple ones. So here you go. This program is taking a packet from the network, and it's trying to read in a field from the packet into this array, this destination array. And so this destination array, you can think of this as I think this happened in a DNS parser, where it says, I'm going to read in the DNS name, so like www.yahoo.com. I'm going to read that into this buffer. It's going to hold a string. And then I'm going to get the length of the name from the packet. So this getLength field says, parse the packet and give me the length of this packet. All right? So that's what that code does. It turns out this is an 8-bit length field, and this can be signed or unsigned, but it turns out that they used a signed number here. And this is the downfall of this thing. So it's using a signed character. It's like 8-bit length field, it's a signed character. You know, what could go wrong? But then it's going to call this SNPrintf. This is a string printf. And what this does is that instead of printing to standard out, it says print it to another buffer. So it says print this thing to this buffer destination. This is the length that you want to print from this field. And then I want to print that as a string. And the source is wherever the pointer is in the packet. Okay? So the issue, what is the issue here?
It's only going to go up to 127.
Yeah. So this, when you read this as a signed character, really you only get 0 to 127. What happens if you do
You're going to get a negative number,
128? This gives you a negative number, this length,
which doesn't make sense.
which doesn't make
But
sense.
it gets converted probably to an actual length. It's much larger.
Oh yeah? Where does it get converted?
S in printf.
Yeah, okay, so
That's
now
gonna
this
get-
is negative, so okay, I 128, my string is 128 bytes, so now I've blown up that integer, that signed integer, because I'm past it, so that most significant bit is set. Then I call this SNPrintf. Where is it going to get blown up?
Some random memory location.
No, but like, where does the problem happen?
Right inside of there. When length goes in, it's going to get promoted to a regular.
Yeah, when length goes in, it's a signed character. It gets promoted, all ones. And then this size t, this is an unsigned integer. So now that all ones gets cast into an unsigned integer, just like 4 billion. And then you're going to print a 4 billion length string from the source to the destination.
Which means you could write over all of your memory.
Pretty much. That's game over for this particular DNS server.
Like, that's how you can print out passwords and stuff too. Once you get out of that
That,
range.
yeah, this is Heartbleed-ish. Very
Okay.
Heartbleed-ish,
Oh,
which is
that's
an exploit that I think I covered in the first lecture. Very much like that.
So the only thing you have to change is that just put a larger number than like. the
Yeah,
size.
make it unsigned if you know, like, when you're reading this.
So size underscore t is an integer.
It's an unsigned integer.
Unsigned integer.
Yeah, and of course it would be. Like, why would you have a negative size? This is where the error really happened. You did not specify this as being unsigned when you got this, and so then you top out at 127 as being the largest positive integer going through there. So that mismatch right there causes the overflow. And I actually, this is the text that explained what you guys just deduced.
I would have assumed too, since it's another length function, that it just returned unsigned because you're not going to get a negative length anywhere on that get.
Oh yeah, and this could.
I just would assume that. Oh, it's.
This could return that, but then this still is a signed character that will get promoted when you do that. Yeah. So yeah, it doesn't even matter if this is returning signed or unsigned. It's still getting. Yeah. So this is another DNS parser vulnerability. There are 2 bugs here in one, which is why I'm going to show it. So here it's giving you this buffer, and it's asking you to generate from this buffer this name. And the buffer has got this format. Here's a length, followed by the length of that sub part of the name. So 4 bytes test, and then 3 bytes Jim, then 3 bytes com, and then a null to terminate that. And so this code is parsing this to generate that. Simple, right? So the name is going to be stored here in this name string. The count is going to store the count that I read from these fields. And then this index field is going to be sort of pointing to individual parts of this array to get the information back. All right? So the first thing that you should note is that this buffer is 256 bytes. And if you look anywhere in this code, do we look to see if max length is getting blown up? No. So error number 1 is that there's no length check anywhere for this name string. So that's rule number 1. So you could completely blow this up with a name that's more than 256, and there's nothing in this code that checks. The other one, which is the casting one, if you look at this count's an integer, but what we're doing is, because we know that this is a byte, these are bytes, we're saying that